Hi everyone. In today's session, we will solve a problem to find minimum in sorted and rotated array. So let's first understand what is sorted array and what is a rotated array. Okay. So here we can see that this is my sorted array, completely sorted in ascending order 1, 2, 3, 4, 5, 6, 7, 8, and 9 and 10. Okay. And if I were to rotate it means counterclockwise direction. This direction means if I were to take the last item and push it at the first place. Okay. So what will happen? It will look like 10, 1, 2. Okay. Like this. So we call it one time rotated. Okay. And what if we rotate it again? Means put the last item at the front again. So it will look like 9, 10, 1, 2, and this. Okay. So it will look like this. So 9, 10, 1, 2, 3, 4, 5, 6, 7, and 8. This is two times rotated because two items we have moved one by one, two items at the beginning. Okay. And similarly, this is three times rotated because one by one, this is one item from the end was put at the beginning, not two items and three items. Correct? So all of these are sorted and rotated array, and there can be more number of rotations. Okay. It's not just that it will be three times rotated. Okay. So this is sorted and rotated array. Let's move on. Now, to understand how to find the minimum in a sorted and rotated array, because we can do a linear search on this. Okay, this is my sorted and rotated array. Okay, we can do a linear search, but linear search will take how much time? Order n, correct? But we want to optimize this and we want to do it in order of log of n. So the information here given is the array is already sorted and then it was rotated. Okay. So somehow one approach can come in our mind that maybe binary search can be applied because anyway we want to reduce the time from n to log n, correct? So let's try that. Okay. Let's try that. This is my and so when we were applying the binary search, what are we doing? I hope you remember the binary search. Okay. So we had two pointers, the start pointer, the end pointer, and we were finding the mid by start plus and by start divided by 2. Okay. So 0 plus 9. Okay. For 0, 9, start and the mid will become 4. Okay. This is my mid. And what is happening now? So this M is dividing the array in two equal halves. Okay. Keep that in mind. It is dividing that array in two equal halves. And half is sorted, one half is sorted, while the other half is unsorted. Which one? This half is sorted, while this half is unsorted. We can clearly see that, right? Because 8, 9, 10, then 1 and 2 is here. From this start to mid index, this half is unsorted and this half is sorted. Okay. You can see from mid to end, it is sorted, and from start to mid, it is unsorted. Like this. We have marked the sorted and unsorted parts. Now, we can see that our minimum element is going to be found in the unsorted part only, right? Because after rotation, one half of the array is going to be sorted and one half is going to be unsorted. That is going to be the condition always, okay? And because our target is to find the minimum, so we should keep this fact in mind that it is going to be found in the unsorted part only. This one is my minimum, okay? So for each iteration of binary search, what we will do? In binary search, for each iteration, we were discarding the another half, okay? Where, that was not worth searching for, right? That's what we were doing. So when we have the fact that minimum is going to be in unsorted part only, then we should discard this sorted part. Okay, so that's what we are going to do for each iteration. Okay, this will be our initial approach. Okay, now moving on. Let's say some cases to make sure what we discard the sorted part in correct way. This is also a problem to be addressed, because discarding is okay, that's the logical part, but how to discard, that is also a question, so that we don't lose any information. Like here, This is my array. Okay, the rotated part is written in red color and the unrotated is white. Okay, so this is my sorted part, and this is unsorted part. So if I am going to discard this part now, what I'm going to do? Just simply because I will discard this. So I will, in the next iteration, my start should be here, correct? From index number 5. So from start equals to 5 to end equals to 8, it have my minimum lies here. Yes or no? So no information loss. Okay, no information. We are not losing any information. So putting s equals to m plus 1 for discarding is correct in this scenario. Okay, now moving to the next scenario. What is the next scenario? Here in this next scenario, though this part start to mid is unsorted, okay, but at the same time mid to end is sorted. And as we just establish the fact that we will discard this sorted part, correct? So what are we going to do? Discard this. So what we did in binary search was earlier we put end equals to mid minus 1, means this is going to my new end, this will not be. So if you can see here, what is happening when I have only this much window of the input, I have completely lost my minimum item. Lost minimum item. Okay, so we can't discard this part in this way. Okay, I mean, if we are discarding the right hand side, we can't discard that in this way. I'll tell you why, but let us stick to this point. So instead of doing e equals to m minus 1, we can do e is equals to m only. Okay. Okay, so now making both cases, taking both cases simultaneously. Okay, here in case number 1, we were discarding the sorted part, but the sorted part was in the right left hand side. Okay, so we were just doing start is equals to mid plus 1, and it was completely okay. But here if we were doing end is equals to, because if we were going to make this our new end equals to mid minus 1, we was losing this minimum part, right? So we can't do that. That's why we put e is equals to m only. Now you can see this relation. If it is the left hand side, we will just put s equals to m plus 1. If it is right hand side, we will put e is equals to m. I'll show you why. Because there must be a question. You must be thinking, why this difference in discarding method, correct? Okay, so to answer that, let's make one more observation. And what is that observation? See here, we have case number 1, case number 2, and case number 3 also. This time, we have not marked according to the binary search. Okay, this time I have marked only the rotated part and unrotated part. Though after rotation, the rotated part will be sorted in itself. I mean, both parts are sorted in themselves, right? See here, this is 4 times rotated array. I mean, previously it was sorted, then rotated. So 7, 8, 9, 10. They are the rotated part, but still they are sorted in themselves, right? And this 1, 2, 3, 4, 5 is also sorted in themselves. That's why unrotated part I have marked as part B, and the rotated part I have marked as part A. Okay. Now in all of these cases, these 3 cases, the size of these parts, we can conclude that the size of these parts need not to be equal. Okay, they can be of any size. Okay, unlike in binary search, I'm showing this so that you don't get confused. Okay, this was start, this was end, and this was mid. What was happening? The left hand side and the right hand side were of almost same size, because mid divides them in two equal halves. Okay, but here the condition is a bit different. But at the same time, I want to take one thing in the notice also, that is, in whatever I mean, how many rotations the array have doesn't matter, but the minimum is going to be found in the part B or the unrotated part only. Okay, like here, and see here. This is the minimum item. I mean, this is one minimum. It is always going to be found in the part B only. Okay, so keep that in mind. We'll come to that. Why we have made that? I mean, a fact, proper fact. Okay. And adding, just to add one more point in that, though this part is part B, okay, minimum is going to be here only. Okay. So when we were applying the binary search part now, start, mid, and you can see that. So here we can see that from this mid to the end part. Okay. If you were to check if this part is sorted or not, what will we say? Sorted, correct. And if you were to check this part, if this is sorted, then this will automatically be unsorted, correct? So what we usually do is we will just put what and equals to mid minus one. Okay. So it will become here. My end will become here. And this time I'm not losing my minimum item. Okay. But what happens if it happens here? Because mid is at 4, it's at end, and this is my start. Okay. If I am checking, okay, if I am checking mid to end, it is sorted. This is my start. Okay. Sorry. I put the E. Okay. Mid to end, it is sorted, while start to mid is not sorted. Okay. If it is sorted, and I will just discard this part because this is sorted. Okay. In that case, what will happen? I'm losing my part B completely. Okay. By putting end is equals to mid minus one. I'm putting my part B completely, and my minimum is lost also. That's why I came one step forward to show you in this part A, part B form, the rotated and unrotated side of the array. Okay. So to just to avoid this condition, to lose this information, what we do is E is equals to M only. Okay. Now that's the relation I wanted to show you. Okay. Now we know how to discard and how binary search can be applied here, because in binary search we were discarding the one half of the input. Okay. With each iteration, here also we are discarding the sorted part. Okay. With each iteration, the difference is that when it's the left half which is sorted, we are discarding it as s equals to start equals to mid plus one. But if it is the right half that we need to discard because it is sorted, then we are doing and equals to mid only, not mid minus one, so that we can retain our minimum item. Okay. I showed you how this is working. Okay. This is not just something random. Okay. Now let's move to the pseudocode part. Okay. Here in this code, the same binary search code, initializing the start and end. Okay. Then while loop, same condition, start is less than equals to end, and then finding the mid. Okay. Correct. Here that part is missing because one part is missing because we don't have any key. Okay. We don't have any key to compare with. Okay. And we don't have any key because the question is also saying to find the minimum, but we don't know the value of minimum. That's why. Okay. So that part is not here, but that's exactly why we would have to wait till this whole binary search completes. After the termination of this binary search only, we'll get the answer, because we don't have anything to compare if it minimum or not. But with the logic, we can end the loop at the minimum. Okay. That's how it is going to be narrowed down. I will show you how. So this is the condition. As I told you now, we will see which part is sorted and which part is unsorted. So this condition is checking unsorted part overlapping with part B. Okay. So array of mid is greater than array of end, means it is unsorted. See here, if array of mid, yeah, see here, this is going to be my mid. Okay. and this is going to my end. So array of mid is as greater than array of end, means this is unsorted part, right? So that's what we are doing here. If it is unsorted, okay, means we need to discard the sorted part. Okay, for that, what are we doing? If this is my right hand side, okay, means if right hand side of middle is unsorted, then left side of middle is going to be sorted. So discard the sorted part, which is left hand side. Okay, so what are we doing? Start equals to mid plus 1. In the else part, means the right hand side of the input is not sorted. I mean, it's sorted. Sorry, because we are checking for unsorted now, means it is sorted. So if it is sorted, we need to discard it. And how were we discarding the right hand side of the middle? Not m minus 1, we were doing equals to m only. Okay, so that's how it is working. And then this whole while loop will be completed. Okay, it is going to run in that way. I am marking this star on this while condition because I want to show you something, and if it is going to change or not. Okay, and at the end of this whole while loop, our, I mean, one of the pointers will be pointing at the, or both of the pointers will be pointing at the minimum item. Okay, start or end. Okay, so anyway, if your requirement is to get the minimum item in the return, then you can return array of start. Otherwise, if you want the index, then you can return s only. Okay, that's what it is about. So let's try run this. Okay, and here if you are going to try run, let's say start is equals to 0. Oh, I think I should not use this now. This is my start, this is my end, and this is going to I mid initial now. And equals to 9, then mid is equals to what? 4. Then what I am checking? Array of mid is greater than array of end or not? Array of mid is 10. Is 10 greater than array of end is 3? Yes, correct. 10 is greater than 3. So what will I do? Start equals to mid plus 1 means 4 plus 1 equals to 5. Correct. So my new start will become here, and I will discard this part. Okay, new start is here. Start equals to 5 and equals to 9. Then my new mid will be what? 7. Correct. So this is my new mid, and what I am going to do when I have found my mid, again checking if it is unsorted or not. So array of mid is greater than array of end or not. So what is array of mid? 1 greater than array of end 3. Is 1 greater than 3? False. So I am in this else condition. Okay, in the else condition, e is equals to mid, which is 7. Okay, so instead of here, e will point to here. Okay, now start is equals to 5, e is equals to 7. Then what will the mid? Mid equals to 6. Correct. Mid will become 6. Now array of mid is greater than array of end or not? Let me point the mid first. Yeah, here. Okay, so array of mid is 0 and array of end is 1. So is 0 greater than 1? False. So what will happen? E is equals to m, which is 6. Correct. So again this e will be discarded. Okay, let me change the color, and this will be my new e. S equals to 5, e is equals to 6, then m equals to 5 again. Correct. 6 plus 5, 11 by 2, 5 you will get integer value. Correct. So now array of mid is, I mean, this is going to my new mid. Let me correct it. Okay, so array of mid is -1. Is it greater than array of end, which is 0? No. So what will happen? And is equals to mid, which is 5. So now start equals to 5, and equals to 5, mid equals will become 5. Correct. This and will be discarded and it will be here. Okay, now start, mid, and end are all at the same places, which is -1. Correct. Still we are okay because start is less than equals to end. Correct. So now what will happen? I will check array of mid with array of end. Array of mid is 5, array of end, sorry, array of mid is -1, array of end is also, I mean, end is the same index, so it is also -1. Is -1 greater than -1? False. And on false, what is happening? And is equals to mid again. No changes. So start equals to 5, e is equals to 5 again, and mid equals to 5. So isn't it looking like some infinite loop? Correct? This is not gonna end. So to avoid that, what we should do is, instead of start less than equals to e, this should not be here. Instead of this, it should be start less than e only. Okay, that's why remove this equal to sign. Okay, that way it will terminate. And see, when this is terminating, my start, mid, and end both all are at this index 5, and which is -1. I mean the item which is minimum. So either you can return -1 as an item, or you can return 5 as index. Okay, so that's what it is doing now. But this code is going to fail if items are repeated. Okay, this code was good until all the items was unique. Okay, unique items, it was good. But what if when the items are repeated? Okay, let's check it. See, here is my test case. Start equals to 0 and is equals to 6. What is my mid? Mid is 3. Okay, this is start, this is my end, and this is my mid. Then array of mid is greater than array of end. That's what I am checking here, correct? So what is my array of mid? It is 2 is greater than 2. False. 2 can't be greater than 2. What will happen? Start equals to mid plus 1 means 3 plus 1 equals to 4. So it will come in this part. See? Oh, sorry. Little mistake. 2 is greater than 2? No, it's not. So I am in this else part now. So instead of start equals to mid plus 1, it will be end equals to mid. Okay. So end will be pointing here. Correct? Now start equals to 0 and is equals to 3. What will be my mid? Mid equals to 1. Correct? This will be my new mid. Now array of mid is greater than array of end or not. 2 is greater than 2 or not. False. So again I'm in this else condition. So e is equals to mid. So instead of here, this will point to here. Okay. Start equals to 0, end equals to 1, mid is equals to 1 by 2, 0. Correct? So this is my new mid. What will happen? Array of mid is 2. Is it greater than array of end? 2? No, false. So what will happen? E is equals to mid. What will happen now? S equals to 0. My new is also here. E is equals to 0. So what will happen? Start equals to end. Therefore, terminate. And on termination, where my start and end pointers are pointing at this location. Is this minimum? No, not minimum. Correct? Therefore, fails here. This algorithm fails here. Now I will show you what else we can do. Okay, why is it failing and what else we can do? See here. It is failing start and this was mid. Okay. Initially, it was okay to discard this part because anyway, it is not unsorted. Okay. Because see, 2 start equals to 0 and equals to 6, mid is equals to 3. So 2 is greater than 2, false. So that's why we were in the else part and we did else equal and equals to mid, correct? That's what we did. But then from here, the game became complex. Start equals to 0 and equals to 3. What will be my new mid? Mid equals to 1. Instead of this, my mid is here. Now, array of mid greater than array of end, 2 greater than 2, false. So end equals to mid. So I have just lost my mid item. Yes or no? I have just lost my mid item. Sorry, minimum item. I have just lost my minimum item here. because though 2 was not greater than 2, okay, so in the else condition we can say that what was written here is nothing but if am is greater than array of e, then in else condition it will be am array of mid is less than equals to array of e. In the else it will be assumed only. Okay, so let's check one condition first. Let's check for the lesson condition. For here, when s is here, mid is here, and end is here. Okay, is 2 less than 2? That's also false. Again, uncomparable, I mean undecidable. We can't reach. Now the only condition left is equal to part. Is 2 equals to 2? Yes, correct. Right? So if this condition is correct, this means we can't decide if this part is sorted or unsorted. So that way, what we are going to do is, instead of changing this middle, no change. Okay, no change. Why? Because middle is the main idea in the binary search. Okay, so we are not going to modify this. So instead of that, what we did is, okay, if it is equal, let's say their items are repeated, but if it is sorted and rotated also, then let's check what is the item just before that. Okay, so to do that also, not just checking item before that, we are now just decrementing the range also. Okay, we are discarding, I mean instead of discarding this whole part, we are discarding this item only. Okay, by doing what? By putting e is equals to e minus 1 only. Okay, means decrementing e. So if it is, I mean these are equal now, we will do e minus minus. So this is my new e, this is my mid, and this is my start. Okay, let me mark again, this is my mid and this is my start. So what will happen? Now we can again check now if array of mid is greater than array of start or not, array of end or not. Yeah, it is, because array of mid is 2, which is greater than array of end, which is 1. So it is true. So now we are here again. Okay, start equals to m plus n 1, sorry, so means start will come here. Now start and end are equal, so this will terminate and 1 will be your answer. Okay, so see here, that is the case. Let's write it down. Start equals to 0, end is equals to 6, mid is equals to 3, start and this is my mid. Okay, mid equals to 3. Then what will happen? Array of mid is greater than array of e, 2 is greater than 2, false. Now what I am checking in else if, sorry, I think this lesson should not be here. Sorry, it should be less than. Okay, yeah, it should be less than. And what I am doing is, now if 2 less than 2, no. If 2 is equals to 2, correct, that's what in the else condition. So e will become 6 minus 1 equals to 5, correct. That's how it is going to happen. That's how it is going to happen. E will become here, and if it is here, then what is my new mid? Start equals to 0, e is equals to 5, mid is equals to 2, correct. My new mid will be 2. Now array of mid is 1. Is 1 greater than array of end, which is 2? No. Then 1 less than 2, correct. So what will happen? E equals to m. So e will be here only. E is equals to m. In that condition, see, it is converging for something good. Okay, s equals to 0, e is equals to 2, m will be 1. This is my m, new m. Okay, so what will I check? Array of m with array of end. So 2 is greater than 1, correct. So what will happen? Start equals to m plus 1, which is 2, correct. So start will also become, no, start will become here, because 1 plus 1 2 now, 1 plus 1 here. Now what will happen? Start equals to 2, and equals to 2, therefore terminate. And on termination, what is happening? Where are we? We are at the index 2, and this is my minimum item. So either we can return the whole item or just index only. Okay, that's completely depend on the requirement of the question. So I hope you people understood this all. Okay, and so let's meet in next part of this. Thank you, everyone. This is how you find the minimum in the sorted and rotated array. Okay, that's all for this session. Thank you.